Now we want to take a look at the area between curves computed with respect to y. What this means is that the function is better represented with respect to y than with respect to x, in that when you look at the function, you have one clear function on the right side of the region and one clear function on the left side of the region. And then you're going to write the functions in terms of the variable y instead of the variable x. So this means you actually solve for x and you have x equals, and then on the right side, you have some expression involving y. And you do that for each of the two functions. And then your limits of integration become y values. So it goes from the lower y value to the upper y value. Now, when you're doing this, of course, you will have to change the differential as well. The differential will have to represent the one that is being changed, which is always the narrow end of the strip, and that's going to be dy. So when we're looking at this, we're looking at dy being this distance here. So when we're looking at the height of the strip, we can see that it is the right function minus the left function. And then the differential is dy, and we integrate from the lowest y value up to the highest y value. So from the lowest strip to the highest strip, function on the right minus function on the left. So we're going to partition the interval on the y-axis and use horizontal rectangles instead of vertical ones. So when we do that, that means that delta y, and I don't like the way they've written it, I like it out here at the side, which is where it actually belongs, right? This distance right here, that narrow end of the strip that you see right there, that narrow end right here, that is delta y or dy, which is the same. And then this function on the right-hand side that you see here, that's one of the functions expressed in terms of the variable y. And the blue on the left is one of the functions expressed also in terms of y. And then the length of that strip becomes the height of the rectangle. So when we find the area of the rectangle, we're multiplying the distance between the two narrow ends times the length of the narrow end, which is dy. So we're getting u of y1 minus v of y1 times dy, right? So the area of one rectangle becomes u of y1 or y sub I at some special point minus v at the same y value. And all of that, that's the height multiplied by dy. So this is the length of the rectangle, and this is the width of the rectangle. So we have length times width, which gives us area. And then, of course, we repeat that process for each of the strips from the lowest y value at C to the highest y value at D. And then we add them all together. Then we take the limit as the number of rectangles goes to infinity, giving us a Riemann sum. Now, the Riemann sum, the limit of the Riemann sum gives us the definite integral. So when we integrate this, we're going to have the definite integral from y equals c to y equal d, and then we're going to have the expression u of y sub y minus v of y times dy, all right? So those are going to be expressions in terms of y, right? And this is a limit of a Riemann sum. Here's the formula that you can see right here. So you have the integral from c to d of u of y minus v of y dy, which is the same as splitting it into two integrals. Now, when you're splitting it into two integrals, what you're actually computing is the area of the rectangle coming all the way back to the y-axis. And then this one, this narrow little bit right here. So you take the taller one minus the shorter one, which gives you the area of the strip in between, all right? So again, it's the same idea as what we did with respect to x, but now with respect to y. All right. Now, if the values of C and D are not given to you, then you'll have to find them. And this will be because the curves intersect. So then you'll be looking for the points of intersection again. So you set the equations equal to each other, or you substitute for one variable in the other, and you solve for where they intersect. This time we're looking for the Y value where they intersect, not the X value. So chances are that what you want to replace, what you want to substitute for, is the X variable in terms of Y. And then we'll do the right curve minus the left curve. Again, this area will always be total area, not net area. So it's going to be strictly positive. Let's take a look now at example 7, continuing from where we were before. So we want to take a look at this. We have find the area between the curves given by y squared equal 4x and g of x equal 2x minus 4. So y squared is going to give you a parabola, but it opens sideways. And because this is positive, it's going to open to the right. So we have a right opening parabola, and then 2x minus 4 is a line. So we have a right opening parabola and a line. Now you can either graph them by hand, or you can use Desmos or your graphing calculator to sketch a graph. But when you get the graph sketched, it should look like this. So you can see here in purple, we have our right opening parabola, which has the purple marker, and the black marker is for the line 2x minus 4. Then we look for a region that's completely trapped by the 2. So again, we're looking for a region that is contained completely within the hot pink region. So we can see that it's that area right here that is completely trapped. So this is our target area right here. And we want to find that area. So what we're going to do then, and I'm going to shade the area. If I can get it shaded without going outside the lines too much. I was never much of one for staying inside the lines in the preschool and kindergarten. I was always kind of an outside the lines kind of gal. Okay, so when we're looking at this, we're going to try to find the area. Now, why would this be a bad problem to do with respect to x? Because that's the key thing. Why would we do it with respect to y instead of with respect to x? So we have our two functions here, y squared equal 4x and y equal 2x minus 4. Why wouldn't we integrate this with respect to x? Think again about how it works when you go with respect to x. When you go with respect to x, you make vertical strips so that the differential is dx. And then when you draw your vertical strips, and I think I'm going to undo what I just did, and I'm going to draw for you a vertical strip so you can see. What do you notice about the vertical strips? If we were to do a differential of dx and write the integrand in terms of x and use x values for the limits of integration, what do you notice about this first strip on the far left? What graph is it touching at the upper end and what graph is it touching at the lower end?
It's only touching the y function
It's
and
only
completely missing the
touching,
x.
it's only touching that parabola, right? It's only touching the purple. It's not touching the black. So if you were going to do this one, you would have to solve for y. If you solve for y, right now you have y squared equal 4x, and then you could take the square root of both sides, and that would give you a plus or minus on the other side. So you have y equal plus or minus the square root of 4x, which of course is plus or minus 2 square roots of x. This upper curve is the positive 2 square roots of x, and this lower curve is the negative 2 square roots of x. And I don't know why I put another 2. Okay, so in other words, you have to split the parabola into two pieces, the upper arm, which is the positive arm, and the lower arm, which is the negative arm. The first bit goes from the upper arm to the lower arm. So you'd have upper arm minus lower arm up until where it intersects. So you would have to find this intersection point right here, which we're going to have to find anyway, but you would have to integrate this from where it intersects from the beginning at 0 over here to where the x value where it intersects. And then the second half, you would have the upper arm of the parabola minus the line. Does everybody see that? So it would be difficult because you have to split it into 2 regions and you would have to integrate each region individually. Let's just go ahead and do this example. We're not going to do the integration, but we're going to write down what the integral would be if we did it with respect to x. So the first thing we need to find is that intersection point. So I have y squared equal 4x, and I have y equals 2x minus 4. So I could take the y and I could substitute in there, and that would lead to 2x minus 4 quantity squared equal 4x. Multiplying out, this would give me 4x squared minus 8x minus 8x minus 16x plus 16 equal 4x. And then I would have to subtract the 4x, which would lead to 4x squared minus 20x plus 16 equals 0. And then we could divide everything by 4. Dividing by a constant is okay. Dividing by the variable is not. Do not divide by the variable unless there's no other choice. So then we have x squared minus 5x plus 4. And that factors into x minus 4, x minus 1. So we have 2 possible places when x equal 1 and when x equal 4. So our integral would have to go from 0 to 1, and then we would have to do the upper arm, positive 2 square roots of x, minus the lower arm, 2 square roots of x. And notice that gave us a double negative, and then differentiate with respect to x. All right, so that would be the upper minus the lower. Now that's only the first part. That's not all of it. That would only get the following region shaded. That would only get this part right here done. And then to get the other part, we would need to integrate from 1 to 4, which is the other place where they intersect. So this is at 1 something, and this is at 4 something. And then we would have to integrate with the upper curve being the 2 square roots of x and the lower curve being the line. So then we would do plus the integral from 1 to 4 of the upper curve, 2 square roots of x, minus the line, 2x minus 4 dx, right? And this would be our integral if we want to integrate it with respect to x. It's doable. Don't get me wrong, it's doable, but it is a lot of work, and we have a kind of a nasty variable or a nasty expression, the 2 square root of x, which is never as much fun as just an ordinary x. Now, how could we redo this in terms of y instead of x? So looking at it in terms of x gives us 2 regions, one in yellow and one in hot pink, and we have to integrate them separately because they have a different curve on the top as they do on the bottom in the 2 different regions, and that's with respect to x. Notice that your limits of integration are x values. Notice that the integrand itself down here, these are expressions in terms of x, and the differential is dx. All 3 of those things go together. X values for the limits of integration, integrand is x expressions, differential dx. Now, if we look at this same region that we've got right here, is it always the same curve on the right as it is on the left? So do I have one curve and one curve only on the right side of the region and one curve and one curve only on the left side of the region?
Yes.
What's on the right? Okay, so Juan says yes. Juan, what's on the right?
The line 2x minus 4.
All right, so the line is on the right and the parabola is on the left. Because it's only one function on the right and one function on the left, it's one region if we integrate with respect to y. So now I'm going to erase the vertical strips and the dx. And now what I want to do is I want to draw horizontal strips. If I can get the right color. So here's a horizontal strip, and here's a horizontal strip down at the bottom, and here's one kind of in the middle. Do you see how all three of those horizontal strips touch the same curve on the right and the same curve on the left? But because they're horizontal, the differential, which is always the narrow end, is now dy. That means that when I compute the integral, I have to use y values for the limits of integration. So I'm going to have to compute what the y value is when x equals 1. But I can plug that into either equation because this is where they intersect. It's on both. So use the easier one, 2x minus 4. So when x is 1, I get 2 minus 4, which is -2. So this value here would be -2. When x is 4, I get 8 minus 4, which is 4. And that matches up with where it looks like it is on the graph. So when I'm writing my integral, I'm going to go from -2 to 4. And these are y values. And over here, I'm going to have the differential dy instead of the differential dx. Those are two of the three major pieces to integrate. The last bit, of course, is the integrand in here. And because the differential is dy and the limits of integration are y values, this has to be an expression in terms of y. So to get it in terms of y, what we need to do is we need to take these two equations and solve for x. So y squared equal 4x becomes x equals y squared over 4, and y equals 2x minus 4 becomes y plus 4 equal 2x, which is y over 2 plus 2 equal x, right? Does everybody see how we've solved these two original equations for x so that we could get the expression written in terms of y? It's the same curves, it's the right curve and the left curve, but now we only have one region. So when we shade it, it's only going to be just the one, all the same color, because we have the same curve on the right and the same curve on the left. So now we're going to do the line minus the parabola. So our line, and I may have to scoot my differential over a little bit. So the line is the expression y over 2 plus 2 minus the parabola, which is y squared over 4 with respect to y. All right. And hopefully this makes sense to you, what we're doing and why we're doing it. Are there any questions for me so far? Okay, then let's go ahead and integrate this one. Well, I try to get my, oh, that's not working. There, that's better. Okay, I'm getting a little warm here. Okay, so let's take and do the integration now. We can simply apply the power rule. We may need a little more space. So this is going to lead to 1/2 y squared over 2 plus 2y minus 1/4 y cubed over 3. And it all needs to be evaluated between -2 and 4. So this would give me 1/4 times 4 squared minus negative 2 squared plus 2 times 4 minus a negative 2 minus 1/12 times 4 cubed minus a negative 2 cubed. And that would give us 1/4 of 16 minus 4 plus 2 times 6, double negative is positive, minus 1/12 times 64. This is going to be a negative 8, so it's going to become a minus 8, which makes it plus 8. So this gives us 1/4 of 12. This gives us 12. And this gives us 1/12 of 72, which ends up being 3 plus 12 minus 6, which comes out to be 15 minus 6 is 9. I'm getting 9 square units of area. And then the last thing you should do is you should go up and look at your picture and make sure that you buy that. 1 square unit would be 1 little square of this size right here. And it looks like I can easily clock off at least 1, 2, 3, 4, 5, almost 6. And then I've got some more space still in there. So yes, it does look like actually I can do probably most of 7. And then I've still got some regions I haven't included. So 9 seems like a reasonable answer. Okay. 9 square units. All right, let's do another example. So the key, of course, is to make sure that you know when to do one method and when to do another method. This one is given the area between the curves given by x equal y squared minus 3 and g of x equal 1/2 x. So 1/2 x is a line. And again, we have y squared, which is going to make this a sideways opening parabola. And it's been shifted left 3. So when we look at this sideways opening parabola here, let's imagine doing it with respect to x. To do it with respect to x, you draw vertical strips, which is kind of opposite, but that gives the differential of dx. Notice right away when we do that, that the strip at the farthest left is from parabola to parabola. And the strip in the middle and all the way to the right is between the upper arm of the parabola and the line. That tells us we need at least 2 integrals to go with respect to x, which makes it not a very attractive choice. The other dead giveaway that you might want to go with respect to y is that this equation is already solved for x. When it's already solved for x, it might be easier to go with respect to y instead of with respect to x. So now we're going to erase these vertical strips for integrating with respect to x, and we're going to draw some horizontal strips, one low, one middle, and one high. Notice that in all 3 strips, what we have here is we have the line, which is on the right, and the parabola, which is on the left. So again, if we do this with respect to y, we only have one region. So we're going to integrate with respect to y, and we have this region right here, which is trapped between the 2. On the exam, you are allowed to use Desmos, and you can copy off what you have on Desmos. You can just take a screenshot of it, and you can paste it onto your exam. That's fine. Or you can hand draw what you see on Desmos. So now we have the differential dy, which means that we need these points of intersection right here where the 2 curves intersect. So we need to solve where they intersect. We have x equal y squared minus 3, and we have y equal 1/2 x. So the first thing I'm going to do is I'm going to solve for x in both cases, and I'm going to substitute the x's equal to each other. So rewriting the second equation, I get y equal, or 2y equal x. setting the x's equal to each other, I have 2y equal y squared minus 3. Moving the 2y to the right and flipping the 0 around, I get y squared minus 2y minus 3 equals 0. Then we factor y minus 3, y plus 1. Now we are going with respect to y instead of with respect to x. So we really don't need the x coordinates. What we need are the y coordinates right here. We really don't need the x coordinates. We're going to be integrating from y equal low to y equal high. And then we're going to have expression with y minus expression with y. And the differential is going to be dy. And this is going to be the right function minus the left function. All right, so that's the expression that we're looking for. The low value for y to the high value for y. The right expression in terms of y minus the left expression in terms of y with a differential of dy. So we have both of the functions solved for x, so we have them in terms of y. And now we can find the intersection points, which are y equal 3 and y equal -1. And looking at the graph, we have y equal, did I do that right? Oh, y value. The y value is -1 and the y value is 3, all right? So far we know that we're going to integrate from y equal -1 to y equal 3. Because it's all in terms of y, it's not required that you put the y equal. I'm just doing it for emphasis. All right. Now we need the right function in terms of y. So looking at the graph, we have the line on the right, and the line in terms of y is x equal, and then the other side is the expression in terms of y. So it's 2y minus, and now we have the parabola expression solved for x. So this is in terms of y, minus y squared minus 3. And then the differential is dy. Do notice that when we subtract the left function, it is in parentheses. You're going to be changing both signs of the second function. So when we do this one, we get, and you can write this directly below if you leave enough space, 2y minus y squared plus 3. And then you can integrate directly. So you have 2y squared divided by 2 minus y cubed divided by 3 plus 3y, all evaluated between -1 and 3. So the 2's cancel, and we end up with 3 squared minus -1 squared minus 1/3 times 3 cubed minus a -1 cubed. Careful with the parentheses, don't squash your work up, spread it out. The bigger it is and the more white space, the fewer mistakes you're going to make. And one thing I noticed on the quiz is there were a lot of mistakes in the evaluation of the definite integral. And it wasn't because it wasn't set up correctly, it was. It's because you cramped it up, but that's partly my fault. I didn't leave enough space. Okay, so then plus 3 times the quantity 3 minus a -1, which is a double negative, so that's a 4. This is going to give me 9 minus 1. This is going to give me 27 minus a -1, which makes it plus. So this gives me 8 minus 1/3 times 28 plus 12, which gives me 20 minus 28/3. I can write 20 as 60/3 minus 28/3. You guys check my arithmetic. And I'm getting 32/3. square area. So almost 11 square units, right? Not quite 11 square units. Then look back at your region and see if you buy that. I've got most of 1, 2, 3, maybe 4, 5, 6, 7, 8, 9. Yeah, I'll buy that. It's a little less than 11. That sounds reasonable, right? Okay. All right, let's do another example. We have one more to do. Find the area between the curves given by y equals y minus 2 quantity squared divided by 3 and g of x equal 8 minus x. So this second one, let's go ahead and write it in a better format. We have y minus 2 quantity squared over 3. The y minus 2 quantity squared is going to tell us right here that this is a parabola. And because it's going to end up y squared, it's a sideways opening parabola. So again, we see the sideways opening parabola as a common feature of area between curves in problems, homework problems. So we also have a line which is negatively sloped, 8 minus x. When we look at the region, if we imagine trying to do it with respect to x, we would be drawing vertical strips from the far left, one in the middle, and then over to the far right. If we did that, notice that I have parabola over parabola until I reach the intersection up here, and then I have line over parabola the rest of the way. That means to do it with respect to x, I need two integrals because I have two regions. If I want to erase those vertical strips and go with respect to y, I need to draw one at the lowest y value, draw one in the middle, and one at the top. In all three cases, I have the line on the right and the parabola on the left. That makes it easier to do with respect to y instead of with respect to x. Plus, this function up here is already solved for x, and that will make it easier for us to substitute it into the integrand part of the integral. We can go ahead and take this function here and write it as y equals 8 minus x. And then solving for x, this is going to give me x equal 8 minus y. So now I have both functions written in terms of y. Now what we mean by in terms of y, we mean we've solved for x in one place, and the right side is an expression with the y variable in it. So now we have the two pieces we need for the integrand. We know the differential will be dy. Those are two of the three pieces. The last piece that we need is we need to know what the intersection points are from the low to the high. Specifically, we need the y values. So we want to get rid of x in the expression and have y only. So now we're looking for these intersection points right here. And again, you can't take it directly off the graph because you can't solve it precisely enough. You'll never tell the difference between 7.1 and 7.01 or 7.11. You can't see that. So you're going to have to do it algebraically. So we're going to take our two expressions, y minus 2 squared over 3. And our other expression, which is 8 minus y, and set them equal to each other. This is basically x equal x. So when we have x equal x, we have these two next to each other. And then I would multiply through by 3 to get rid of that fraction. This would give y minus 2 quantity squared equal 24 minus 3y. Then you're going to have to multiply out the y minus 2 quantity squared So I get y squared minus 4y plus 4. And then I can move the 24 minus 3y to the left side. So I'm going to subtract 24 and add 3y. And that gives me y squared minus y minus 20 equals 0. Whatever you get on the exam should factor. If it doesn't factor, then you've done something wrong, because I didn't give you anything that wasn't relatively easy to figure out. Okay, so you shouldn't need the quadratic formula for these. So y minus 5, y plus 4. Although you can always use the quadratic formula to find them if factoring is not one of your best skills. Though if it's not one of your best skills, you need to work on that, because factoring is hugely important in all 3 calculus courses. So this gives me y equal 5 or y equal negative 4. So then I go back up here to the picture and I look at this. I'm not finding the x value. I'm finding the y value of negative 4. And then up here, not the x, but the y value of 5. Yes, that is 5. Yes, that looks like negative 4. So I have confidence in my solutions. And now I write the integral from y equal negative 4 to y equal 5. And I need the right function, which is the line, which is going to be 8 minus y up here, minus the parabola, which is y minus 2 squared over 3. So I have the line 8 minus y minus y minus 2 squared over 3. Now I want to show you something that you can do with the third term here. It may not have occurred to you that you can do this, but it will be faster if you do. So I have 8 minus y, which I can integrate directly. This will give me 8y minus y squared over 2. For this part right here, I can do a u substitution. I can let u equal y minus 2 so that du is equal to dy. And then I can make a substitution. So when I substitute, I need to get out of the negative 4 and the 5. So I'm only going to be integrating these two between negative 4 and 5. And then the second one, I'm going to say when x equal negative 4, u equals negative 4 minus 2, which is negative 6. And when x equals 5, u equals 5 minus 2, which equals 3. So my second one coming over here is going to be minus 1/3, pulling the negative and the 1/3 out. So that's the negative that you see here and the 3 in the denominator. And then we're going to integrate from negative 6 u value to 3 a u value of u squared du. So I replaced the y minus 2 with u. So that gave me u squared. And then I had a dy, but dy is equal to du. So I was able to replace that here. Questions on that? Does that make sense to everybody, what I did? That saves me having to multiply this out and having the 1/3 on each of the terms after I multiply it out. You can multiply it out, just be careful to keep the negative 1/3 on each term. All right, but this saves you a little bit of time. So now let's take some more space so we can finish integrating this. So I have 8y, which is being evaluated from negative 4 to 5. So this is going to give me 8 times 5 minus a negative 4, which is going to give me a 9. So following this on down, this is going to give me 72. Then the second term, I have minus 1/2 times y squared. So I pull the minus 1/2 out, And then I get 5 squared minus negative 4 squared. And this is going to give me 25 minus 16, which is 9. And then I get minus 9 halves. And then looking at the last part, which is this u substitution, I have minus 1/3. And then I need to integrate the u squared. So I get minus 1/3 u to the third over 3 evaluated between negative 6 and 3. Those are the u values that we switch to. Now the minus 1/3 times 1/3 gives me a minus 1/9. And then I can substitute 3 to the third minus negative 6 to the third. Hopefully I did that correctly. 3 to the third is 27. This would be minus a negative 216, which is 6 to the third. And now I need a calculator. I'm reaching the end of what I can do in my head. Okay, so 27 plus 216 comes out to be 243. So then we have equals 72 minus 4.5 plus 200. Oh, wait, and then we've got divided by 9. So we need to take 243 and divide by 9, which is 27, and it's subtracted. So minus 27. And that's going to give us I got 40.5 or 81 halves. Do I have confirmation from anyone else? If you multiplied it out, did you get the same thing? Hopefully you did. Okay. Now let's look at the last few problems out of this homework set. These are not ones that we're actually going to integrate. These are instead just ones where we want to determine whether to go with respect to x or with respect to y. So if you go with respect to x, notice that your integrand is written in terms of x, your limits of integration are x values, and your differential is dx, and then it's the upper curve minus the lower curve. When you're integrating with respect to y, notice that your integrand is in terms of y, your limits of integration are y values, and your differential is dy, and then it's right curve minus left curve. I know it's a little backwards, isn't it? Okay. So let's go ahead and take a look at some regions right here. This is the area between the curves x squared and y equals square root of x. So if I were to do this with respect to x, I would draw vertical strips from the left, middle, and right. This would be dx. And these are intersecting. I'll go ahead and tell you that they intersect at 0, 0, and they intersect up here at 1, 1. So if you're looking at this one to go with respect to x, we would integrate from 0 to 1, and then we would have the upper curve, which is the square root of x, minus the lower curve, which is x squared. So this would be upper square root of x minus lower x squared with respect to x. Now, if we want to go with respect to y, we need to take our strips and we need to draw our strips horizontally from the low to the middle to the high. And in this case, they're also only between the two curves. This time we have x squared on the right and the square root of x on the left. However, we have to solve for the variable for the variable y. So we have y equals the square root of x which would become x equal y squared. And then we have x squared equal y, which becomes x equal plus or minus the square root of y. So if we were going to do it with respect to y, it would actually be more work because we have to find the integrand functions in terms of y, and that's more work. So then we have to decide which of the two arms that we have here, the plus square root or the minus square root. We have the upper arm, which is the plus square root. So this is x equal, oops, wrong one, the right arm, not the left arm. So this is x equals the square root of y, and this is x equals y squared. All right. So if we're going to go with respect to y, we would go again from the lower y value, which is also 0, to the upper y value, which is also 1. But these are x values on the first one, and these are y values on the second one. And then we would do the right curve, square root of y, minus the left curve, y squared, with the differential dy. All right. So as far as integrating goes, it doesn't make much difference. The integrand functions are identical, except for the variable is different, but the form of the functions is the same. But having to solve the original equations for x in terms of y is more work. So I would do this one with respect to x. What about the next one? X equal y squared minus 4 and g of x equal x over 3. The fact that they've already solved this one for x in terms of y kind of tells me that maybe it would be better to go with respect to y instead of x. So when I'm looking at this one right here, if I were to visualize going with respect to x, and I'm not going to write that one out, I would have upper parabola minus lower parabola, and then upper parabola minus line for the rest of it. So going with respect to x would divide it into two regions. Going with respect to y, though, would always be the line on the right and the parabola on the left. So I would definitely do this one with respect to y. All right, that one is definitely better with respect to y. And then we have two more, I think, to take a look at. We have this region here, and it's trapped between the curves x equal y squared minus 3y plus 12 and x equal negative 2y squared minus 6y plus 30. Again, the fact that it's solved for x is kind of a hint that this would be better done with respect to y. When you look at the region, you can see that it would. This is actually, I don't know if I can blow this up enough to make it clear. All right. If we look at this thing, do you see where it intersects right here? It has a tiny, tiny little sliver where that purple parabola sticks out past it. So it would be the upper purple minus the lower purple. Yeah, for this tiny little sliver sticking out past that x equal 10 line. And then we would have the blue minus the purple until we got to this intersection, and then we'd be upper blue minus lower blue. So to do this one with respect to x would require 3 regions, not 2, 3. And that would make it extremely difficult. So if I were looking at this one, I've got a little region here of yellow, and then I've got a region right here coming up to this point right here, where it would be upper blue minus lower purple. And then the last region would be this over here. All right, so you can see that you would actually need 3 regions to go with respect to x, and it would be enormously difficult. You would have to take the equation up here and you would have to move x to the right side so it's equal to 0 so that you had 12 minus x, and use the quadratic formula with 12 minus x being c. It would be enormously difficult. This one is far better to do with respect to y. If we go with respect to y, then we always have, if we go from a low, oops, I need a thinner one. If we go from a low rectangle and a medium rectangle in the middle and a high one, you can see that we always have the blue on the right and the purple on the left. So definitely, absolutely better with respect to y, no question, right? So when you integrate with respect to y, this would be one region, right? Much, much better. There we go. Okay, back down. Get a little larger. And then we have one last region. This is a cubic written in terms of y, and this is a parabola written in terms of y. And when you look at this one right here, we've got actually two separate sections. We've got a section up here, which is larger, and then a section down here just above the origin, which is smaller. So we have two regions that are between the curves. If we go with respect to x, again, it would be a nightmare. We would have purple over purple until this intersection point, then purple over blue. But in this region, the smaller one, we'd have blue over blue and then purple over purple. So we'd have 4 regions total that we would have to do with respect to x, which is a lot. With respect to y, we're still going to have the 2 separate sections. So we still have that, but we have the blue curve on the right and the purple on the left, and then purple on the right and blue on the left. So definitely this would be better with respect to y. So this is the end of the section on area between curves. And what we want to do now is we want to switch gears and we want to look at volumes of revolution by disks and washers.